Hi, for this question, the diagram shows a smooth, narrow tube formed into a fixed vertical circle with center O and radius 0.9 meters. A light elastic string with modulus of elasticity 8 newtons and natural length 1.2 meters has one end attached to the highest point A on the inside of the tube. The other end of the string is attached to a particle P of mass 0.2 kilograms. The particle is released from rest at the lowest point on the inside of the tube. By considering energy, calculate the speed of P when it is at the same horizontal level as O, the speed of P at the instant when the string becomes slack. Okay, for this question, we need to find the velocity when the object is here. At that point, I need to find V. So let us suppose this is A and B, and I want to find VB. First of all, by using energy method, I need to find out what's the energy here. We are told that U is equal to 0, the starting speed, the initial speed is 0, therefore I've got kinetic energy as 0. And potential energy at the bottom, we're going to take it as 0 as well. So what we have is only elastic energy. Now, to be able to find the elastic energy, I need to know the length of the extended length, because it is attached here, of this elastic. The extended length is basically, let's say the arc is equal to 0.9 pi. And the difference between the natural length and the extended length is going to be equal to the length, which is 0.9 pi, minus 1.2 meters. And so this is the extended length. The difference between the extended length and the natural length is x. Why I need x? To be able to find the energy, the elastic energy. To find the elastic energy, I'm going to use lambda times x squared divided by 2L. So that's going to be then lambda, which is the modulus elasticity, which is 8 times x squared. X is all of that. And you divide by 2 times the natural length, 1.2, and should be able to get 8.829 something. So the only energy I've got here, the initial energy basically, is 8.83 joules. Now from here, let's say we go to the level horizontal with O. So we want to find V here. So we should use the principles of the conservation of energy. Basically, the elastic energy is equal to all the energy at this point here. I've got the kinetic energy at B, and I've got also, this point is B, and I've got the gravitational potential energy at B, plus the elastic potential energy at B as well. Now from here, I'm going to say 8.83 is equal to the kinetic energy at B, which is half 0.1 times VB squared, plus gravitational potential energy is mgh, 0.2 times 10 times the height, 0.9, plus the elastic potential energy, which is 8 newtons times the length of the arc minus the natural length, which is basically 0.9, and this is 90 degrees. Okay, so this is basically pi upon 2, so that's going to be 0.9 times pi upon 2 times g, which is 10, hang on a second, no, times minus 1.2, and all of that to the square. This is not the gravitational potential energy. We talk about elastic potential energy. I'm sorry for the confusion. Divided by 2 times the natural length, 1.2. Okay, so we've got then 8.83 is equal to, this should be 0.2 here because the mass is 0.2, and so 0.1 V B squared plus all of that, which is 1.8, plus all of that. So here I've got and times divided by 2.4 basically, 0.152249. So v square b is equal to 8.83, take away everything here, so 1.9522 and so on, and then divided by 0.1. Okay, so 68.775, and if we take the square root of that, we should be able to get what we're looking for. Let's take the square root, and that's what we're getting, 8.29322. Therefore, this is no longer square because we've already taken the square root on the other side. We've got it as 8.29 meters per second, and that's the speed at b. Now, in the second part of the question, I need to find the speed of the object when the string is slack. Suppose it comes all the way up here, and this is where it is slack. Alright, so now I need to find v. Okay, so basically I've just drawn under the diagram to make things easy, and here we go. Right, so we want to find the velocity here. Remember, we're going to use the principle of conservation of energy again. Alright, so basically I need this angle here. So I'll tell you in a moment why I need that angle. So when the string is slack, it's going to return to its natural length. Natural length is 1.2. So with that here, 1.2. And so this is the length of the string now. It's slack, it's not moving up anymore. And I can use circular measure to find theta. So arc length, which is 1.2, is equal to 0.9 theta, meaning that theta is equal to 12 divided by 9, and that's going to be 4/3. So I got that angle in radians. Now, with that angle, I can find this height here. Okay, so this height, small height, remember this is 0.9, but this small here is the adjacent to that angle. Using trigonometry, I got that one as, let's say that this is let's say y. So y is equal to 0.9 cos of theta, which is cos of 4.4/3. So 0.9 times the cos of 4/3, and that should give us 0.2117. Now I can find the total energy here using the principles of energy conservation. This initial energy, the elastic energy, is equal to the gravitational potential energy and the kinetic energy, so half mvc squared plus GPE, the gravitational potential energy. We don't have any elastic energy anymore. Why? Because the string it's in its normal length now. Okay, so this is 8.83 is equal to 1/2 times 0.2 and Vc squared plus the gravitational potential energy is mgh, 0.2 times 10 times the height. The height is 0.9 plus all of that. So plus 0.9, and we got 1.1117, so 1.117138, etc. So let's do that in a calculator, and here we got 0.1 v square c plus all of that, so multiply by 10 times 0.2, 2.2234, and so on. Rearranging all of that, v square c is equal to 8.83, take away 2.2234, and so on, divided by 0.1. So 66.065. So Vc is equal to the square root of 66.065 0.0657 and so on. So let's take the square root of that, and we should be able to get 8.128. 8.12808 and so on. So VC is equal to 8.13 meters per second, and that's the speed when the string is slack. Take care.